First of all, I want to thank John for organizing this. This seems to be like a great opportunity just to communicate, ideas without having to wait for the major conferences. So, I also see a lot of familiar names in the list, so I want to say hi to everyone. For those that we haven't chatted in a while, but it's always a pleasure to talk to you and to probably get your feedback about this topic. So let me get started. So this is an interesting problem. When I came to Argonne, I started working heavily on power grid, and I was feeling a little bit, at some point, it's a very interesting problem, but I was lacking a little bit of the chemical engineering type of excitement. So I came across this natural gas project because I'm interested in optimization of infrastructure systems, and especially the interdependencies type of problems, and how that is opening doors for optimization and optimal control and things like that. So today, the first disclaimer is that the area of gas pipeline optimization, especially the practitioners know this, it's a very complicated domain. It's a big domain. A lot of optimization has been done. So by no means I intend to say like we're doing something drastically different, but what I think is interesting is to start to understand again how does optimal control and predictive control start fitting into the new ways that the gas pipelines are being operated, because nowadays they're facing new types of uncertainties and things like that. So let me move on this topic. There are many types of optimization problems in gas pipeline systems, like in almost any infrastructure type of problem. The particular problem I'm interested in right now is something called line pack management. Line pack management is a very interesting optimal control problem, where essentially what you want is that, imagine you have a very simple system. This can be a large network, but let's start with something simple. But imagine that you have a given supply flow of gas. The pressures that we're talking about here are like 50 to 70 bars, so it's reasonable pressures. Out of the supply flow, you basically want to satisfy a certain demand at the end of the pipeline. So these pipelines are very, very long, so they can have like 1,000 kilometers long. So this can be very, very long. And at some point along the pipeline, you're going to have a set of compressors. In this case, I'm just showing you one, right? So just to simplify. So what I want to optimize, or what I want to figure out, is what is the policy for this compressor boost. So I'm going to have a time horizon. So I want to know how much pressure, additional pressure, I'm going to put in that compressor to satisfy the demand. The demand is going to follow a certain profile. And we want to satisfy all sorts of constraints, like we want to satisfy discharge pressure constraints, suction pressure constraints, and eventually, satisfy demand. Now, the big issue in gas pipelines is that you don't know the demand with full certainty, because one of the things that happens is that some of these nodes, like this demand node, might be connected to a big power plant, something like a combined cycle plant. And these combined cycle plants, they might come online, offline, depending on electricity markets. So what happens is that you might have a very steep, sudden increase in demand that almost looks like a step function. So the operator needs to be ready to satisfy that. So one of the powerful things about gas pipelines that is also very helpful is that there's actually it's a compressible fluid. So what you can actually do is to pressurize the system, build up gas inside the pipeline, and essentially use that inventory inside the pipeline, or storage inside the pipeline, to actually satisfy the demand at given times. So that is one of the things that these systems have. They have a huge storage capacity. They have a lot of flexibility. So this is the problem that I'm interested in. And I'm interested particularly from a stochastic point of view, in the sense that, well, if we can model somehow the uncertainty of this demand, If we know at what time is it going to come, if we have at least some idea of what is a suitable time, what is going to be the shape, then we want to prepare that inventory to satisfy or to ensure that we're going to have enough demand in any possible scenario. Right? So that is the basic setting. Why are we looking into this problem? I honestly think that one of the gas pipelines, of course, the gas market exists by itself, but one of the big reasons why the gas market is so important for all of us is because it's tightly connected to the power grid. So one of the big issues that the power grid right now is facing is that they still have very drastic fluctuations of prices. And these are non-negligible fluctuations. So here I'm showing you some prices for the Illinois system in 2009. So this is very typical to observe that you get these very high spikes of electricity prices. So in Illinois we have an average price of $40 per megawatt, but this price can go as high as 200 to 300 in certain periods. Prices can actually become negative, which seems a little bit absurd, but it's actually true, because what happens is that you have periods or moments. It doesn't have to be a long period of time. I mean, you can have time instances of 5 minutes, let's say, where you actually have too much electricity and you need to pay people to use it. So this is not uncommon to have. So this is an interesting problem. Volatility in the power grid is also observed not only in time, but also you have it in space. So when you have periods of scarcity, because you have, for example, transmission lines that are congested, or you have power plants that cannot ramp up or down sufficiently fast, then you get these periods of either scarcity or excess, right? And that's what drives prices. So here I'm showing you a map of the prices for the Midwest area in the U.S. So what you see is that when the demand is well behaved and predictable, things look nice, you know. So you have almost a field of prices. So in the United States we have almost a price per every node. So these are locational marginal prices. So you see here that we have a price of around $14 per megawatt. All right. During a period of high stress, the price field just distorts completely, and you can have very weird price profiles. So, for example, here what you see, and these are real prices. So I want to scare you a little bit. But essentially, you have, for example, somewhere around here in Iowa and Wisconsin, you can observe a price of around $1,000 per megawatt. And somewhere here in Illinois, we're observing prices that are exactly the same magnitude but negative. So minus $1,000 per megawatt. So what is happening is that nowadays we still have a lot of very, very extreme volatility in prices. And one of the reasons for this is that it's a typical problem that we don't foresee enough how are things going to happen. We don't get ready for it. We don't prepare, and then we end up positioning these power plants in places where they cannot ramp up or down, and then that creates these periods of scarcity, and this creates these very strong distortions in prices. So things are getting worse because of wind power. So the unique feature about wind power is that the uncertainty profiles that it follows is something that we have never seen in history. Demand profiles are actually quite predictable. So there are some uncertainties associated with them, but this is strongly linked to behavior and ambient temperature, and we know that, and people have beaten that problem to death, you know. But the problem with wind power is that it actually depends more strongly on other meteorological factors, and it's a little bit more complicated to predict. So here I'm just illustrating some wind ramps, how typically they can simply go completely from a 50% ramp down of total capacity within an hour. So, and this is one of the reasons why natural gas is becoming very important, because in places where you have a lot of wind power, you also need to have some sort of natural gas type of power plant, because those those power plants can start very quickly. So you are talking about things like combined cycle power plants. So those are called ramping units in the power grid. So I'm essentially trying just to frame why we're looking into gas pipeline optimization. I think that there's these very interesting synergies between natural gas and electricity that open a lot of opportunities for us chemical engineers and optimal control people, and optimization people. So some of the challenges and opportunities of this interaction of natural gas are the following. As I mentioned, gas is essential to enable large adoptions of renewable power because of combined cycle plants. Electricity markets actually drive a large fraction of gas markets precisely because of the real-time market. So actually people that own combined cycle plants are actually looking for periods with the spot price or the real-time price just goes to a very large value like that 1,000. And man, that's when they make their millions of dollars. Seriously, just by operating within an hour, they can make a lot of money. So there's some very, very strong economic incentives there. Some of the challenges is that, as I said, natural gas loads are very different from power grid loads. Natural gas loads, they are somehow connected kind of in a weird feedback loop with electricity markets, because the electricity market is doing what it's doing, and then at some point when they clear the market, they're going to decide that I'm going to allocate this combined cycle plant, and without really very little notice, they're just going to start the unit, and then the gas pipeline operator has to figure out, oh my God, what am I going to do next, right? So this forecasting of this or modeling these uncertainties of demands for natural gas is very hard. But there's some very interesting opportunities here. So nowadays you see the emergence a lot of dual drive compression units. This is something that is relatively new. In the past, most of the compression for these long gas pipelines was coming directly from gas. So they would use some of their own natural gas, burn it, and generate compression, essentially compression power that way. Well, they figure out that that is actually can lead to some very strong inefficiencies, so they decided, well, what if we actually have electricity, but then with electricity you have this issue that you can have very high prices, so they say, well, we don't want to compress and be at the mercy of these very high prices of electricity and all this volatility in prices that I was mentioning. So they say, okay, wait a minute, so why we actually have compressor systems that allow for both type of compression. So we can allow for gas and we can allow for electricity, and we operate depending on what is the competing market of gas and electricity. So kind of a hybrid car. But this opens a lot of interesting opportunities for demand response, because you can actually think, well, the electricity market can actually use these dual drive compression units to make use of that electricity when you have excess. So what that means is that now gas pipeline operators can actually participate in the electricity market and say, look, if I can provide you this many megawatts of potential demand, so similar to how some chemical companies do it, so how about we participate in the market and I promise you to deliver this much demand. So there are opportunities for doing this optimization of natural gas and electricity. Some interesting facts about the power grid, the natural gas network, the transmission network in the US, is that so it is a very sophisticated system. So you have something like 272,000 miles of transmission lines. And on average, you have compressing stations located every 50 miles. So I don't show here all the gas compressors that we have in the U.S. because the map looks very, very interesting. It essentially looks like a very dense grid. But it's one of those interesting things. So the system is actually very well equipped. There's a very strong infrastructure for doing this. That just means that there's a lot of room for optimization as well. So a pipeline of 50 miles can store a lot of natural gas. And this is something that actually surprised me when I started doing some of the calculations. But essentially, you have the equivalent to run a 500 megawatt power plant for at least 10 hours. So if you have a gas pipeline that is long, you can actually compress that system sufficiently enough, right? So you can store a lot of gas. But the issue here is that the transportation delay of natural gas is actually very large. So the typical gas speed in the transmission system is around 30 miles per hour. So if you want to store gas, you better do it very, very well in advance. So for example, I was reading somewhere a number that said that just moving gas from Texas to Illinois will take you 2 or 3 days. So, if you want to optimize natural gas systems, you can. So the big message here is that if you want to optimize natural gas systems, you have this very high domain of optimization that you have to take care of. One is time, because of the transportation delay. So you cannot just optimize for over an hour because you cannot capture the long transportation delay. So that means that you have to be optimizing over a day or probably even more. So that is one of the first things. The other thing is that because the transportation delay is of course associated with the length of the pipeline, that also means that you have to consider very long pipelines, and that means that we have to model those long pipelines, and those are partial differential equations. So there's some problem here with complexity as well. But so there are a lot of opportunities, but a lot of complexity. So let me move on into the next thing, which is how do we first model these systems. And the most important thing that I think that I want to send a message is that my model is not going to be complete. My objective here is to have a model that represents what you can potentially do with line pack storage in natural gas systems. So I essentially I just want to communicate what are the essential features of this model, why the model is so complex, and what you can do with it. So let's move on. So don't pay attention to all the equations at the same time, because I always make this mistake, and I think it's part of my nature of putting all the equations there. But essentially, let's go line by line. Essentially, we're talking about here of a large network. The network has these balances in each one of the nodes, so you can think of multiple links and multiple nodes. The links are going to be the pipelines, and the nodes are going to be potentially compressor stations, or just simply nodes where the pipelines have their junctions. So here I'm defining these inlet and outlet flows for each one of the pipeline. So each one of those pipelines have a flow coming in and a flow coming out. For a particular node, you can actually have supply flows, and for certain particular nodes, you can actually have demand nodes, or demand flows, I'm sorry. So I'm also here specifying these sets. So this set N is the set of all possible nodes in the network. T is a set of times, or time steps. Omega is a set of possible scenarios. So here I'm essentially specifying my physical model for each possible scenario, and later we'll figure out how do we actually make the decision under uncertainty. Now, the dynamics of each one of these lines, which makes this network different from power grid networks, is that you actually have dynamics that are significant, is that you have conservation and momentum equation. So in one dimension, it actually looks something very simple. It's computationally complex, but it's actually not that terrible. So essentially, you have here on the left the derivative of pressure with respect to time, and this is defined for each possible link and for each possible, right, like a point in space. So K is now my grid points in space. And on the right-hand side, essentially what you have is the derivative of flow with respect to x, the independent variable x. So that's the space dimension. And this constant C1 It's a very complex constant that depends on a lot of things that can depend on temperature, can depend on gas gas properties and things like that. So I'm not going to show it you here. I try to keep it simplified. And then you have also the momentum equation, which is derivative of flow with respect to time. Then you have the derivative of pressure with respect to space here. And then here you have this term that actually makes things very complicated. So this is a nonlinear term where one of the things here is that you see this absolute value, that essentially what it's telling you is that flow can actually change direction in these pipelines. So you can actually have flow reversal. So if you change the pressure of one of the compressors, right, and you make it larger than the pressure at the other point, then you can actually have the flow reversing. So it is possible for this. So here what I'm assuming is that the direction of the flow is already given, and that's going to simplify the problem significantly. But this issue of flow reversals is very, very important, and I don't want to underestimate the importance of this. Especially this becomes very important when you have networks with potentially loops and things like that. So you have to be careful about how do you deal with those. So then essentially I have my PDEs for each one of those lines. I have my network balances, and so now how do you connect both? So you have these boundary conditions where essentially tells you, well, the flow leaving a particular link is actually going to be the outlet flow of that particular link, and then the flow entering is going to be the inlet flow of that particular link, and that's how I couple. I could eliminate those two constraints just by substituting directly in the balance, but this is, I think it's easier to appreciate the model this way. And you do the same with pressures. Now, with pressures, you have that the pressure at the end of one link or pipeline is actually these pressures at the nodes. The pressures at the nodes are fully specified by the node balances. So we were going to get into the degrees of freedom analysis of this. So these are not independent variables. So the pressures are actually state variables. They're not controls. And then you have that the pressure at the entrance of what link is actually the pressure of the sending node. Then I also specify the way I model compressors is the following way. I say the pressure I can have two types of links. One of those links is an active link, and an active link is one where you can potentially inject additional pressure through a compressor. And I have passive links where you essentially don't inject any pressure, right? So those ones are just interconnectivity. So, and then you have the famous equation, right, that for calculating the compressor power, essentially you're looking at a type of compression equations, and you basically have the ratio of the compressor output to the compressor suction, and this multiplies the flow. So these are equations that I think all of us are familiar with. Now this model is specified for each possible scenario. You have time and space dimensions. So let's move on. What makes this problem interesting from an optimal control standpoint is how do you actually, what are degrees of freedom? What are controls and what are my states? This becomes very important because when you have a DAE system, for certain types of model it's easy to specify initial conditions. But for certain types of problems, it's actually very hard to specify consistent initial conditions. So this is why you have to go to the trouble of characterizing the model. So essentially, the variables that you have in the system, this is the total number of variables. So I have, you don't have to remember all these details, but essentially it's 2 times the number of links times the number of discretization points in a space, plus 2 times of the number of links, number of nodes, number of supply flows, number of demand flows, and number of active compressors. The number of equations is that many. So what that means is that the number of degrees of freedom is the number of supply flows, the number of demand flows, and the number of compressors that you have. Typically, the operator does not have control over supply flows. The supply pressures. The supply pressure, someone else is sending gas for him, and the supply pressure is already fixed. So that actually kills 1 degree of freedom, or a set of degrees of freedom, and that just leaves the degrees of freedom to be the total number of demand flows and the total number of compressors. So what are the implications of this little analysis? Well, one of the issues here is that you cannot fix demand flows. So you might think, well, I want my system to operate and I'm going to fix the demand of what I want. Well, if you do that, then, and on top of that, you say, I want this demand flow and I want it at this pressure. Well, it turns out that if you specify those two constraints, the system does not have enough degrees of freedom. That is impossible. So there's no way of satisfying the full set of constraints if you want to be overly aggressive. So what this means is that typically people what they would do is they say, well, I want my demand flow to be fixed, and I'm going to allow for a range of demand pressures that I'm going to allow you to be around. This range can be very narrow, but I'm not going to just fix it for you. So that is important thing. So if you fix the flows, then what turns out is that the supply flows and the demand pressures actually become algebraic states. And this is actually counterintuitive, because you might expect where a supply flow is a control. Well, in this case, it's not. Once you specify the demand flows, your supply flows become states. You have no way of touching them, right? So the controls are really the boosts for the controls, all right? So we have characterized, so in a typical situation, the compressor additional power or compressor boosts are the controls. The second implication is that, okay, so in my total number of controls are just really my compressors, what that means is that I actually have very few controls and I have a lot of states, because I have as many states as the number of grid points that you want to discretize your pipeline. So if you want to discretize the pipeline by 100 points, you have 100 states, but then you have 10 segments of that pipeline, right? So you might have up to 1 million states easily. So this is not unheard of, right? This is the typical problem that arises in PDE constraint optimization, that you actually have a very large state dimensionality. So what that means is that turns out that you actually do not have that much flexibility in terms of how many degrees of freedom you have, but the system itself might give you a lot of flexibility, and that's something that we want to investigate later on. I'm going to show you some case study. Now, the other interesting implication of this is that if by characterizing the DAE, what that means is that I can actually specify my initial conditions by simply imposing the steady state equations at the first time step, and I just fix the controls. And so that is basically what John, do you want me to answer some of these questions? All right, so I'm just going to keep going.
Yeah, so Jeff has one. Sorry, I was muted. Jeff had one question. Are pipelines operated as a single entity, or are there competing financial interests?
That is an excellent question. So most of these infrastructure systems, they're operated by utilities. So you might have people that own a certain segment of the pipeline. So you actually do not have probably the ability to optimize the entire system, right? So you are only allocated certain domain. So there are competing effects here. There are definitely competing effects about who delivers gas where. So there are markets for this. All right. So I'm gonna keep moving. So yeah, please. I'm looking at the chat here. So and we can always just keep going offline with more questions if you guys want. So I'm just gonna keep moving. So where was I? Yes. All right. The objective function, and this is a very interesting problem because Okay, so this is a very complex PD constraint optimization problem. The nonlinearity is strong. You have a lot of variables, a lot of field conditioning. So you have to be extra careful into how do you actually want to enforce your constraints, because these problems tend to be ill-posed. So what that means is that you might have actually multiplicity of solutions, things that give you the same objective function, and then the solver struggles a lot into doing this. But one of the most important thing here is that how do we actually enforce the constraints? And this is where constraint softening is actually quite important. So actually I don't enforce the demand flow as a constraint. I actually enforce it in the objective function. The reason is that there's really no way that, because of the dynamics, that you can actually enforce the demand at each point in time. Because just think about it, if at a certain point in time there's a step function for the demand, then essentially you're always going to have this transition in the dynamics where you cannot just fully satisfy the demand. So that constraint becomes very, very troublesome, especially when you have these very steep variations of demand. So that's why I put it in the objective function. The other thing that I put in the objective function are the terminal constraints. And the way I specify the terminal constraints is a little bit different to what you will think you will do it for an optimal control problem. I'm essentially enforcing that the entire profile of pressure for all the pipelines at the final time has to be exactly the same profile at the first time step. And I'm doing that for pressure and for flow. The interesting thing is that for a PD constraint problem, you cannot enforce this as equality constraints simply because you don't have enough degrees of freedom. So I was mentioning that we have this degrees of freedom shortage, right? So think about, if you have 100 degrees of freedom and you discretize your pipeline by 200 points, then essentially you have no degrees of freedom. You have 50 variables less degrees of freedom, so the problem is over-constrained. If you send that to an optimization solver, the solver is going to say, oh, no, I cannot deal with this. So this is interesting from an optimal control standpoint, because you actually need to decide a subset of variables that you want to actually enforce, and then let the rest of the state follow for that terminal constraint. So in this case, it was not numerical convenience, but it was simply that there's no way of imposing these terminal constraints as equality. So now these terminal constraints, I'm going to explain a little bit later, but these are very, very important for gas for the operator. But let me move on. So here what I'm defining is the objective function for each possible scenario. All right. Now you want to optimize a single objective function. You want to optimize an objective function for each scenario. So I'm using this metric. I'm using this objective function that is a mean risk type of objective function, where you have the average or the expected value of this cost function. So I just evaluate this cost function and take the expectation over all the scenarios. And then I have this C-bar risk metric. Now, C-bar is a risk metric for those that are not familiar. C-bar is a very interesting risk metric because it has some very interesting computational properties. You can actually compute this property rather easily, and one of the easily features of it is that it's actually a sparse metric. So, for example, the risk metric, the traditional risk metric, is actually a metric that is really hard to optimize for the optimizers because it introduces density. So just think about, you take the expected value of bar phi omega minus the expected value of the same variable, and then you raise that to the square. All right, so the objective function is really dense. So it's actually non-trivial to the variance, the typical risk metric. So CVAR computationally, it's much more tractable computationally. The other thing about CVAR is that the reason why I'm putting a risk metric here is because I want to mitigate scenarios that might actually have a very large cost, right? So the operator might see certain scenarios that might actually hit or might actually impact the economic of the system significantly. So what you want is to actually position the system in such a way that you figure out that. So I have John. So John is asking, could you elaborate a little bit more on why you think it is computationally difficult to compute the variance? Yeah, John. So essentially, what happens is that, unfortunately, I cannot write it down here, but just think about. So the variance is, the way you're going to define it is the expectation of bar phi omega minus the expectation of the same variable, or bar phi, raised to the square. When you take the Hessian of that, the Hessian turns out to be very dense. So that introduces a very dense, it's a small block, but it's a very dense block inside the Hessian matrix. So when you throw that to an optimization solver, the solver has the sparse linear algebra inside the solver tends to suffer from that computationally. So what is happening with the typical variance is that it's just that you are introducing a lot of coupling into your Hessian matrix, and the saddle point system inside the linear algebra then becomes a little bit more complicated. With CVAR, it's not the case. So that's essentially one of the reasons. We can always keep talking about this if you want in more detail. So basically, so essentially, let me just keep moving. So I'm not going to elaborate on this, but essentially, this is the type of metric that I'm using. You have other types of constraints, but these are typical operational constraints, I will say, but you have to take them into account. So you have your supply pressures constraints. So you want someone is telling you what is your supply pressure. You have to enforce that. Then you have these constraints that are actually used to enforce the initial conditions, and I have suction and delivery pressures. So I have all these. These are state constraints that you have as well. I'm sorry, I messed this up. This is not initial conditions. These are pressure constraints. You also have that amount of compressor power that you have in each station is finite, right? So you need those constraints. The most interesting constraint is non-anticipativity. Now, non-anticipativity constraints are interesting from a optimal control standpoint, because non-anticipativity constraints, what they mean is that the full intention is to guarantee that you actually come up with one control policy that is going to optimize all the scenarios, right? So you are not allowed to optimize for each possible scenario, because that will involve the fact that you have perfect information. So what you actually have to enforce is that you actually have one control that you have to implement right now, as you expect, as you are foreseeing your uncertainty. Now, the interesting thing here is that this is a nonlinear dynamic system. So you actually fix the controls, and you actually enforce same control for all these scenarios. It is possible that actually you do not get the same state at a given time, and this is just because of the nonlinearity of the system. So you actually have to verify computationally that this non-anticipative constraint is actually doing what it's supposed to be doing. So let me move on into the case study, because this is gonna hopefully just illustrate everything that I've been talking about. So this is a case study that I got from Richard Carter, which is he works for a company in Houston doing gas pipeline optimization. They've been doing it for almost 20 years. But this is a system that resembles something, a kind of typical scenario. So basically what I want to show you here is that how much flexibility you have in the system. So I want to just convince you that this storage capacity that you have in a gas pipeline is actually non-negligible. And I want to insist that that has very strong implications into what we can do with these pipelines beyond just optimizing them, right? Like what we can do to help the power grid and things like that. So I also want to show you how does the dynamics, what are the dynamics, how does the system behave based on different types of policies. The policies that I'm going to be evaluating are the deterministic policy, where essentially you go with a forecast of demand, and I'm also going to go with the more typical one, which is the worst case policy, what people use in robust optimization. So we have three policies: the stochastic optimization, the one that we're working on. Then you have the deterministic and the worst case. What is interesting about CVAR, CVAR actually has this property that you can tune a parameter that allows you to recover a worst case policy. So CVAR, you can actually think it as well as a generalization of robust and determinist, somewhere in between robust and stochastic. So that is a very nice feature of CVAR as well that I forgot to mention. So the system that I have has 1,600 kilometers. The diameter is around 0.9 meters, so this is a big pipeline. You have 13 nodes and 12 links. We have 10 compressors. The supply pressure is 57 bar. The demand is operates at a nominal flow of 24 million standard cubic meters per day. That's a lot of gas. You have three demand scenarios. I'm gonna right now just to explain how this thing works. You have three demand scenarios. You have a low demand scenario. I'm gonna have a nominal scenario and a high demand. And I'm gonna limit the amount of power that you can actually put in each one of the compressors to 3,000 kilowatts. So I'm going to optimize over a horizon of 24 hours with a 30-minute time step. So that gives you 48 time steps. And I discretize each one of these lines by 20 spatial time steps. So how does the policy look like? This is the stochastic policy. So essentially what you assume in this case is that you actually have a preparation period. So you have a period of time where the operator can start storing the gas, and it has to figure out what's the best policy for doing that, but it allows it to store the gas, and then at that point in time, you assume that uncertainty is going to become revealed. All right, so essentially what you're assuming is that at least you have a period of time where you know how the system behaves, for example, probably at night, and then you say, well, at a certain time, usually peak time for electricity, things are going to reveal about what we're expecting. So this is what you see. The non-anticipativity constraint, what it's doing is saying, I only have one control policy up to this point in time, then uncertainty becomes revealed, and I'm allowed to compute recourse actions after that time step. So essentially that is why you see three different profiles for power. These are two different compressors, and essentially what you see as well is that the compressor returns to the original position. So what that means is that these terminal constraints that I were imposing by essentially fixing the spatial profiles are actually what they're supposed to be doing. They are returning the system for compression and for total inventory inside the pipeline efficiently. I didn't mention that one of the reasons why you want the system to return to the original state is because you have this problem with finite horizon, right? Which is the typical course in optimal control. But the problem here is that if you don't include, there's an economic reason for this. If you don't include a terminal constraint, then what happens is that the system will tend to deplete the inventory inside the pipeline, right? So it already has certain inventory in there, and if you say, well, optimized for the demand for the next 24 hours, the system is going to say, okay, so I'm already storing this much gas, so if you ask me to minimize compressor power, I'm essentially just going to use the one I'm storing. So it depletes completely the pipeline, so it essentially dries it out, and then the system, at the end of the time horizon, it was optimal for 24 hours, but then the system does not have enough inventory to operate for the next day. So this is why it's important to have these terminal constraints. So now this opens also questions about like what is an appropriate optimal steady state, right? So how much inventory you actually want at the beginning of each one of these days, and this is a decision that you have to experiment a little bit more. You need a little bit more computations and trying to figure that out. This is how the actual profiles of flow look inside the pipeline for 3 different scenarios. So I have low demand scenario, nominal demand, and high demand. So you see that for low demand, things are actually pretty stable. So you start at a steady state. So this is this horizontal line, and each one of these level curves is essentially one point in time. All right. So all these gray lines, what they're doing is saying, look, up to the time where I know that the system is certain, I've observed this demand, and the demand is at the end of the pipeline. So you see that each one of these level curves converges to that demand. So what that means is that the system is actually satisfying the demand. Now, in time, because you're actually pressurizing the system and you're building up inventory, this is why you actually have these level curves building up. And it builds up inventory at the beginning, downstream the pipeline and upstream the pipeline. So now, at some point in time, uncertainty reveals, right? So in this case, the uncertainty turns out that the S scenario tells you, oh, okay, so I was at this steady state, I now move to this low demand steady state, which is a little bit higher. So if that happens, then the system has to transition there, and you see that the optimizer is actually what it's doing. It's actually capable of transitioning to the new demand point, right? It's not a steady state, it's actually all dynamic. So in this case, it satisfies the demand. For the nominal demand scenario, it turns out that, yeah, I build up enough inventory, and yeah, I can satisfy the demand scenario, so no problem. And then for the high demand scenario, it's the same thing, but now you see this very strong transience in flow. This is just because if you want to be able to satisfy this very big jump in demand, and this is a non-negligible jump, right? So we're going from 10 million SEM per day to almost 13. So this is an increase of 30%. So you're talking of a 30% increase in demand. So like the pipeline actually has to store a lot of gas to guarantee that the demand is satisfied. So you see that essentially the system builds up a lot of inventory, a lot of flow towards the end of the pipeline in trying to satisfy this. Now this policy that I'm showing you here, this is the perfect information solution. So this is the solution that essentially is, if you could, and this is ideal, you actually do not do this in practice, but if you could foresee each possible scenario and compute an optimal policy for each one of them, then how will the system behave? And these are essentially the profiles that you will see. So you'll see that in each scenario you can satisfy inventory because, of course, you can foresee it. Now, this is the stochastic solution of the here and now solution. So what I was saying, that you have a preparation period, but you're only allowed to compute one policy. And out of that policy, you have to satisfy all those scenarios. So you're a little bit more constrained. So what you see is that the first thing to see is that you can satisfy the demand for the low demand scenario, for the nominal demand scenario, and for the high demand scenario. Now, you see that you build up much more inventory in this case. You see these 3 peaks over here compared to the perfect information. Imperfect information, this is how much you build here, how much you build here, and how much you build up here. So of course, because you have perfect information, you don't have to build up as much inventory. So, but in this case, you have to store much more gas. Something I want to show you is that this is interesting and kind of unique of dynamic systems. That if you build up a lot of inventory, if the low demand scenario realizes, then what happens is that the system has a lot of gas in there, and it has to transition back to the state of low demand scenario. Now this transitioning back is actually non-trivial. This involves a very fast, very strong time transition. So this is kind of unique because in most stochastic optimization models, you say, okay, I'm going to build up inventory and then I just use it. Well, if you don't model the dynamics of that inventory, you can actually restrain the system. I mean, the inventory, you cannot just use it, right? Like that is governed by certain physics. So when we deplete a storage tank, you just don't deplete it like arbitrarily. You actually have to be careful. So let me just move on. The deterministic solution does not work. It's just simply you cannot build up enough inventory, and it's just interesting to see how this manifests. So how this manifests is that you actually tend to dry out the system. So the system is desperately trying to meet the high demand, but it cannot because it didn't build up enough inventory. So this peak you see here is actually quite low. So it desperately tries to move into that case, and you see all this volatility in the flow, and you see that the flow reaches very low level values that I'm not even showing here. But essentially the system dries out, and that just is not feasible. So now the robust solution is interesting, and I have two more slides. This is one of the most striking things that I found in this study so far, because robust optimization is a technique that, it makes sense for risk-averse type of operators. You say, well, I'm an operator, I just want to make my system work, and I honestly don't care that much about economics. I'm paid day by day to actually operate this thing. All right, so I'm going to do worst case. So what I'm going to do is actually, I'm going to build up inventory as if the high demand scenario is going to show up. All right, so I build up a lot of inventory, and because of this dynamic problem that I was telling you, is the fact that it's interesting. So you build up a lot of inventory. So if the high demand scenario shows up, if it reveals, then you are fine and you actually operate very nicely. But if the low demand scenario realizes, then the transition from the high demand scenario to a low demand scenario is very strong, and you actually see here again this issue of dry out, where it's actually not possible to go back or it is possible to go back, but that involves a very strong transition that stresses the system significantly. So there are issues here about how you actually build up this inventory. You cannot just say, I'm going to build up a lot of inventory. You have to be careful about the dynamics, because these are propagating back into the pipeline for over kilometers. So this is why it's important to model these PDs carefully. The C-bar actually gives you something nice, because it gives you something that is, so compare the low demand scenario here. So this is C-bar, and this is the worst case. So it gives you something that looks very similar for low demand and high demand, because you have this trade-off. So this is a nice tuning that you can do with C-bar. It allows you to go both ways. And I think it's a nice tool, at least for the operator, to figure out like where does he want to go. From an optimization standpoint, I just want to tell you the typical story that, it's a complex problem. Now you have PDEs. Turns out something that we have found is that the PDEs actually have to be discretized quite finely, because you tend to underestimate the amount of compression power that you actually need if you don't discretize it correctly. So the differences can be significant. Like I'm observing, for example, here, I'm giving you some comparison of the total amount of compression power if you use 2 discretization points or if you use 20. So you see in one case it's 86,000, 92,000, 91,000, 100,000, and 98,000, 114,000. So you're talking about very significant underestimation of power. So that's just asking for advanced optimization tools. That's something that we're working on. But that is essentially what I have so far. So that's all. Feel free to ask any questions, but if we don't have time, just feel free to write me an email. So, thank you.
Okay. Thank you, Victor. Well, great. Let's go ahead and have a couple questions. You go ahead and unmute your microphone if you'd like to ask, and or you can put it into the chat window as well. I think we have time for maybe 2 questions. Okay, so I just had one question, Victor. Just on the computational results there, could you go back to the slide where you showed the IPF? Now those are like pretty impressive times for 100,000 variables. Are you doing anything with parallelization there, or anything to be able to make that, or is that a single processor?
No, this is really just off-the-shelf IPOpt. We're not doing anything. I couldn't elaborate much more, but essentially, I was more interested in seeing the effect of the discretization on the amount of energy. But yeah, you're right. That you can actually optimize some pretty large system. So in this case, for this case study that I was showing, you're optimizing in 5 minutes. So that's pretty good. Something that helps a lot is the sparsity, of course. For the bigger problems, you start seeing that the times, especially right, if you have 3 scenarios, of course, things are becoming more expensive. But you can even see that you scale better than linearly, right? For 3 scenarios, you require 7 minutes. So the problem here is that the network that I really showed it's realistic, but the size is really not that much, like complicated. I mean, so we're trying to figure out how are we gonna deal with larger networks, and especially how are you gonna deal with much more scenarios. So in this case, of course, it was just for illustration purposes to do 3, but of course you can have several of them. So yeah, we're looking at parallelization, and we're looking at multi-level type of discretization techniques, because the problem is that even one scenario can become very, very complex. So we're doing kind of adaptive discretization inside the linear solver to actually solve the system.
Interesting. Okay, adaptive discretization. Great. Okay, any other questions from the audience?